All right, good morning, everyone. It looks like I am in here by myself for now, so if anybody pops in, you may notice in the recording that people start asking questions. But for now, I'm just going to go start to finish through the practice exam, work out each problem, explain them as I go. So hopefully that will make sense. And if you have questions, feel free to let me know or email me or whatever. Okay, so identify the major ionic species present in an aqueous solution of sodium carbonate. All right, so major ionic species, so this means like what will this separate into when it is in water? And I know it's going to separate into 2 sodiums, and it's going to separate into a carbonate ion. So the important thing to know here is that the carbonate all stays together. You can see a lot of the choices are separating up the carbon and the oxygen. That's not going to happen. I'm going to get one type of cation, one type of anion. Now, there are 2 sodiums. Okay, so anyway, first of all, let me go back to the carbonate. That means I can narrow it down to not D, not B, and not C, right? Because I know the carbonate has to stay together. So my choices are Na2 or Na+, Na2 plus or Na+. And so what's important to know there is that the sodiums will separate from each other. This is just 2 random sodiums not attached to each other. So this is not correct. E is what I want to pick here. Okay, for the number of pi bonds. All right, so what is a pi bond? Sigma bond is the first bond. And then a pi bond is the double bond. And like, so the second bond in a group or the third as well. So this is a sigma, 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 sigma. And then the first one here is a sigma, and the first one here is a sigma. So I have 1 pi here and 2 pi's here. What is the hybridization on the central atom of NO3-? In order to know hybridization, I really need to have a Lewis structure. So starting with the nitrogen in the middle, attaching all 3 oxygens with single bonds, complete the octet on everything. Count up my electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. How many should I have? I should have 5 from the nitrogen. Let me get my periodic table here. All right, sorry if there's a glare, but 5 from the nitrogen, and then 6 from each oxygen. So that's 3 of those, that's 18. And then my negative sign is an extra 1. So this would be a total of 24. So I have too many electrons in my picture. Hopefully we know by now that means I need a double bond. And it looks like that. And now I have a complete octet on everything. And I have the right number of electrons, and it's a negative. So how many, or what is the hybridization on the central atom? How many electron groups does the nitrogen have? It has 1, 2, 3. So the first one is an S, and then I'm going to need 2 more, so 2 P's. Okay, arrange calcium, rubidium, sulfur, and arsenic in order of decreasing electronegativity. All right, so what were my choices? I'm going to just circle them on here. So calcium, rubidium, sulfur, and arsenic. Okay, so then I just need to know my trend. My trend is that electronegativity increases as I go up, and it increases as I go to the right. So this one up here, sulfur, should be the highest electronegativity of the group. And this one down here on the far bottom left should be the lowest of the group. And so let's see what I've got. All right, so one of these where sulfur is the highest, and then I want rubidium to be the lowest. And does the rest make sense? Rubidium, then calcium, then arsenic. Yep, sulfur. Okay, so it would be B. All right, a nonpolar covalent bond would form in which of these pairs of atoms? All right, so nonpolar bond, remember, is a difference in electronegativity of less than 0.4. And I don't even have to do much thinking about this. If I have two atoms that are exactly the same, then they will have an electronegativity difference of 0. All right, page 1 is done. Page 2. All right, consider these species. Which of these species will be paramagnetic? Okay, to determine if it's diamagnetic or paramagnetic, I really need to know I really need to do a molecular orbital diagram. And for molecular orbital diagram, I really want to have, let me see if I have anything helpful. Maybe not. All right, so for molecular orbital diagram, I have like this. I'm trying to remember if nitrogen is where it switches between backwards. See, I haven't studied this recently. Hold on, let me just check my book really quick. All right, so nitrogen, let me see if I can get the camera on here on my book. So what I was looking for is if it's 1 on the bottom and then 2, or if it's 2 and then 1. Nitrogen is the last one that it's 2 on the bottom, then 1, then 2, then 1, like this. I wouldn't focus a ton on like doing a ton of these, but just knowing nitrogen is where it switches and then oxygen is where it's this way is probably enough. So, all right, so I have the sigmas. Sigma, sigma star, pi, sigma, pi star, sigma star. There we go. So that's what they would look like. And I'll need to do one for each of the 3 species. Okay. So for N2 minus, what I want to know, I guess basically for all of these, what I really care about is how many valence electrons do they have. So let's start with N2. So nitrogen has 5 valence electrons, so this would have 10. Nitrogen 2 minus would have 11. It would have 1 extra electron, and then this would have 1 less, so 9, because it's a plus charge. And then I just put them in using all the regular rules. So 11 electrons, 1, 2 on the bottom, 3, 4. Then I go across 5, 6. Then I go back and fill it in, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and then the question is which ones will be paramagnetic. Paramagnetic means at least 1 unpaired electron. Something else is kind of hard to see. There's an unpaired electron, and there's an unpaired electron. And then this one has all of its electrons paired up. All right, how many electrons are in a triple bond? 2, 4, 6. What substance is present in the smallest proportion in a solution? That would be the solute. The solvent is the one that you have more of. Which equation describes a redox reaction? So here's what I'm going to look for. The easiest thing to see would be, actually it's the very first one, I can see it right now. What I see is here's aluminum all by itself, so that has to be a 0. And here it is as part of a molecule, which means it has to have a charge. Even if I forgot what the charge of aluminum is, I know it has to have a charge because it has to cancel out that sulfate. Aluminum is a +3 when it's in a molecule, So here it would be a +3. As soon as I see something change charge, that's it. That's the answer. Hydrogen also is changing charge because here's hydrogen by itself and here it's a +1. And if I look at the rest of these, I can see like potassium is +1 and it stayed +1. And lead is in a molecule, it's in a molecule. Calcium in a molecule, in a molecule. They can change charge in a molecule. I could go back and really check it, but since I found one easily where it looks like it is the right answer, I'm just giving these kind of a cursory look. Here's hydrogen by itself, but it's an ion. This is obviously a net ionic equation because it has charges, so it's telling me that's a +1 and there's a +1. Okay, so that's fine. And then here, this is a net ionic equation as well, and I don't see anything that like shows me for sure that something changed charge. So this is the one that looks like definitely something clearly changed charge, and that's the answer. All right, based on the solubility rules, which of these processes will occur if solution of, all right. Copper sulfate and barium chloride are mixed, and it's easy to get this wrong. I would prefer to just write out the whole like thing and go from there. So like I'm gonna just write it all the way to net ionic equation. Maybe you don't want to do that exactly, but you could at least write part of the way. So what I'm doing here is I'm going to take the cation from one and the anion from the other, and I'm going to make them into a neutral molecule. This sulfate is -2, I know that, so copper here must be +2. Barium is +2 and chlorine is -1, so I'm going to switch them. So copper and chlorine would have to be CuCl2, and then barium and sulfate. And let's see, I need to balance it. I mean, this isn't, oh no, it's okay. It's already balanced. All right, everything's balanced. Okay, so then I just need to figure out the charges, or sorry, the phases. So I know chlorine should usually be soluble. There's only a few cases where it's not. Copper is not one of those exceptions, so that should be aqueous. Sulfates are usually insoluble, and the exceptions were just the, I think mostly just the +1s, right? Or this is mostly, I don't know, barium sulfate looks insoluble to me. So that looks like the solid based on the solubility rules. So the first thing is the only choices here were like this one could be the precipitate or this one could be the precipitate, right? This is something I started with. That's not a product. That's something I started with. And this is something I started with. So if you chose one of those two, it's probably because you didn't understand the question, right? And then I think copper chloride should be aqueous, so that's not it. So that just leaves me with C. Okay, so those are our multiple choice questions. All right. No questions, moving on. Just kidding, there's nobody here to ask questions. All right. Okay, so assign the oxidation number for each atom. All right, so I'm just gonna write them all out. And then write the ones I know. The oxygen, always -2. Remember, it's the charge of just one of the atoms. So even though I have 4, the oxidation number is just for 1. All right, so -2 times 4 is -8, -6, -14. I'm just going to write that in so I know what the charge from oxygen is, and then I can figure out the rest. So in this case, they need to add up to -1, so that must be +7. In this one, they need to add up to 0, so the aluminum must be +6, but that's split over 2 of them, so each aluminum must only be +3. And then down here, they need to add up to -2, so this must be +12, divided by 2 is +6. All right, geometry. So here's geometry, bond angle, hybridization, polarity. Given that this is the Lewis structure, like you don't have to figure out the Lewis structure, I've already given it to you. So this is 3 electron groups, no lone pairs. So if you're using this kind of format, that'd be AB3. That's trigonal planar. The bond angle for anything trigonal planar is 120. If you look at the picture, it looks like 90, but it's not. That's just a Lewis structure, not the actual what it looks like. The hybridization on the central atom, that's based on the fact that there's 1, 2, 3 electron groups. So 1, 2, 3 orbitals. And is it polar? No, it looks like it could be here, but remember it would actually look more like this and they would all kind of pull evenly. So is it polar? No, they all cancel out. Now, if I compare that to this one, which also has 3 things bonded to it, you might say they're the same, right? 3 things bonded, 3 things bonded. But here we have a lone pair. That makes all the difference. So this is AB3E. So this is trigonal pyramidal. Four electron groups is 109.5. 4 electron groups is S and then 3 Ps. And then this one is polar because instead of being like 3 flat like this, it would be like 3 kind of all pointing down. Like, it's not a good visual, but they'd all be pointing down like that. So yes, this one would be polar. All right, balance the following equation. So I'm going to just kind of, I don't know what the strategy is necessarily, but I'm just going to start not with oxygen because there's so much oxygen in all this stuff. It's going to get changed a lot. But I'm going to go with carbon. I need 8. Hydrogen, 9. And then let's see. 16 oxygen plus 9 is 25. And then this is 3 of them. So I need 22 more. So I think I just need an 11 there. And that would be 22 plus 3 is 25. Looks okay. And then remember, don't put a 0 there. If you want to write something, put a 1. Otherwise, you can leave it blank. But 0 is wrong. All right, moving on. The following Lewis structure has an error. Identify the error and draw a corrected Lewis structure. All right, the problem is hydrogen can't have 2 bonds ever, right? It can only have 1 bond. So, and then also I see nitrogen here doesn't have enough electrons, so I'm going to try just moving it like that. That looks like a good place to start. And then now is that correct? The things I want to check to see if it's correct: total number of electrons and octet rule. Remember, you can break the octet rule, but only if it benefits formal charge, and it has to be something that has an empty d orbital, which nitrogen does not. Whoops. Nitrogen has 2 p electrons. There is no 2d orbital, so there's no empty orbital. Nitrogen can never have an expanded octet. Oxygen can never have an expanded octet. So I 100% have to obey the octet rule here. All right, so total number of electrons, 6 from oxygen, 5 from nitrogen. So that's 11, 12, 13, 14. From the hydrogens adding on, so then that's 14 total. Now count in my picture, 2, 4, 6, 8, 10, 12, 14. Okay, that looks good. Octet rule, the hydrogens each have 1 bond. The nitrogen has 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. So that's it. All right, for number 17, 3 Lewis structures, which one is the best Lewis structure and how do I know? So the way I'm going to pick is formal charge. So I'm going to figure out the formal charge of every single atom and then we'll decide. So I'm going to start with the chlorines. Chlorine has 7 from the periodic table, minus 1 for every dot and 1 for every line. So that's 0, 0, 0, 0. 7 minus 6 is 1, 1. Oxygen has 6 from the periodic table, so 6 minus 5 is 1, 6 minus 7 is minus 1, 6 minus 7 is minus 1. And again, if I'm going too fast, it's 1 for every, how many valence electrons from the periodic table? 6, minus 1 for every dot, 1, 2, minus 1 for every line, 3, 4, 5. So 1 minus 5. 6 minus 5 gives you 1. Okay. And then sulfur also has 6, so 6 minus 7 is negative 1, plus 1, and minus 1. Okay. So first of all, I want as many zeros as possible, so that rules out this one. Right? It had too many non-zeros. If I could get all zeros, that would be best, but I didn't get that from any of them, so that's not going to work. So then I have to decide, and the answer between these two is the atom with it, which is more electronegative, should get the negative formal charge. So between oxygen and sulfur, let me erase this. Between oxygen and sulfur, which one is more electronegative? Electronegativity increases as I go up, so oxygen is more electronegative. So oxygen should get the negative. All right. Redox reaction, consider the reaction of solid copper metal in aqueous solution to form copper ions and silver metal, and it gave me a net ionic equation. It says right balance half reactions. Remember, for half reactions, I want to put one element per reaction. There's one. And there's the other. And then I want to balance them with electrons so that they have the same total charge on the left and the right. So right now I have 2 pluses over here, 2 zeros over here. So I'm going to need 2 electrons. Here I have 0 over here and a 2 plus over here. So 2 electrons. So that makes it 0 on this side, 0 on this side. Same there. Then it says clearly label one of your half reactions as the oxidation reaction. So I like to think about reduction first because that's easier for me to remember. Reduction is when it's reduced, so that looks like silver, that's reduction, which means this is oxidation. It's also the opposite of when it's reduced, so when it's going up, which sure enough it is, 0 to 2 plus. All right, draw some Lewis structures. So starting with putting something in the middle and attaching everything. Of course, the thing in the middle can't be hydrogen, so it has to be carbon. So I'm going to start with that. Complete the octet on everything. It's already done, right? Hydrogen only wants 1 bond. The carbon already has 8. Count up how many electrons I should have. Should have 8, 2, 4, 6, 8. So that's it. Easy. NO3 actually, didn't I already do this one? Bam, I already did this one, right? So starting with single bonds, I found out I needed a double bond. But the things that you want to check, if you thought this was right but you weren't sure, the things you want to check, do I have the right total number of electrons, which would be 5, 18, and a 1 extra, so 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And does everything have a complete octet, which it does. All right, and for the last one, okay. So I want the least electronegative to go in the middle. So these are both 1 away from fluorine, but this one's 2 away. So I'm going to guess nitrogen should go in the middle. And I'm going to check my formal charges at the end to see if that seems right. All right, so I'm going to complete the octet on everything. Count out my electrons, 5, 6, and 7, so that's 18. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, so I need to put in a double bond. So first of all, assuming this is right, and I'll check it at the end to see if I could have arranged it better, but assuming this is right, which side should I put the double bond on? Well, if I figure out the formal charges right now, chlorine is good. 7 minus, this is just stray pen marks, but 7 minus 7, this already has a formal charge of 0, but the oxygen doesn't, so I'm going to put it on the oxygen side. And now I have 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14, 16, 18. There we go. 18. I've got all these straight marks, sorry. So this is the right number of electrons. How about formal charges? Chlorine, this is 0, as I said. Nitrogen, 5 minus 1, 2, 3, 4, 5. That's 0. And oxygen, 6 minus 1, 2, 3, 4, 5, 6. So this is all zeros. I don't have to try anything else. Looks perfect. Octet rule is obeyed. Correct number of total electrons, all 0 formal charges. This is great. All right, consider a solution of 0.125 lithium phosphate. What is the mass of lithium phosphate required to prepare 500 milliliters of solution? I'm going to go ahead and convert that right away to liters because I'm going to write this like that. So if I want just moles, which eventually I want mass, but moles will be a good start, I can just multiply. First time I've needed my calculator. Is that true? Wow. Way less than last exam, huh? All right, 0.125 times 0.5. So that's how many moles. To get to mass, I need the molar mass. To get the molar mass, I need to know what lithium phosphate is. So lithium is a +1, and then phosphate is PO43 minus. So that means my lithium phosphate, to be neutral, must be 3 lithiums, 1 phosphate. So then the molar mass is lithium. I'm pulling up my periodic table. Phosphorus and oxygen, 115.8. So now I can take my 0.0625 moles times 115.8 grams per mole, multiply. And I got 7.24. All right, another page done. Consider this molecule. How many single sigma bonds, that does mean single bonds, and then how many pi bonds, hybridization, bond angle. Okay, so I just have to count this carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I counted every single bond for the sigma because when you have a double bond, the first bond is a sigma, so even the double bonds I counted. But now for the pi bonds, I'm just looking for double bonds, 1, 2, 3. Hybridization around the oxygen, it has 4 electron groups, 2 bonds, 2 lone pairs, so that's 4 total electron groups, so that's sp3. And this would be bent with 4 electron groups, that would be 109.5. Again, that's because of the 4 electron groups. All right, here's our limiting reagent problem. It doesn't say limiting reagent, but when they give you 2 different amounts of starting stuff and they ask you how much you can make, that's limiting reagent. So I'm going to do 2 problems. Where I start from each of the reactants, and I'm going to figure out how much in grams CaO I can make, and then whichever one's smaller is my answer. All right, so molar mass of calcium, mole to mole conversion. Oh, let me put in calcium because now 2 moles of calcium on the bottom, 2 moles of calcium oxide on top. And now the molar mass of calcium oxide, which is 40.08 plus 16. Whoops. .08. And now I'll just put that in my calculator. I have 5.88. And now I'll just do it again. For oxygen. All right, so starting with molar mass, now I need to do the moles to moles conversion. Now you can see it's even more important that I have the what it is in the right place, because last time it was just 2 and 2, but this time it's 2 and 1. So if I have it flipped upside down, I'll get the wrong answer. course, I already have the molar mass because I use that up here. Once I'm in calcium oxide, I can use the same molar mass. .81. So those are my two amounts. I just circle the smallest. That's all I can make because then I ran out of something. I'm trying to fit it all on the screen at once. All right, last page. How many moles of iron are present in a cylinder that weighs 25 grams? This is just a this is just an example problem where I just need the molar mass of iron, 55.85. I only want 2 sig figs. 0.45. And then finally, okay, so here's the dilution problem, which what is the concentration of a solution formed by adding 65 milliliters of water to 25 milliliters of a 3.2 molar NaCl solution? So a dilution is M1V1 equals M2V2, where M is the molarity. So for my initial, I can use these numbers. For my final, M2 is my question. My final volume, though, I have to read this question carefully. It could say to a final volume of 65, but that's not what it says. It says adding 65, so my final volume would be 90. Right, adding it together. And then I just solve. It's fine that I put it in milliliters, even though molarity is liters. That doesn't matter here because the milliliters are going to cancel. .8, what do I want? 2 sig figs, so 0.89. All right, that's it. That's the practice exam. Please email me if you have any questions or stop by my office hours or however you can get in touch with me. Otherwise, I'll see you for the exam.